Have you ever pondered the mysteries of the universe and wondered what it's really made of? Welcome to the enigmatic realm of quantum mechanics, where the ordinary rules of physics are defied. Here we encounter the standard particle model, a theory that seeks to explain the tiniest constituents of the universe. But what are these elusive particles, and how do they shape the cosmos we inhabit? Dive into the fascinating world of quantum mechanics and discover the building blocks of the universe. Quantum mechanics, a theory born in the early 20th century, revolutionized our understanding of the universe. In the late 19th century, classical physics was struggling to explain certain phenomena. For instance, the glow of hot objects, known as black body radiation, didn't fit into the existing scientific framework. Enter Max Planck, a German physicist, who in 1900 proposed a radical idea. He suggested that energy is not continuous, but rather it is made up of discrete packets or quanta. This was the first hint of quantum mechanics, a theory that would turn our understanding of the universe on its head. But the story doesn't end there. In 1905, a young patent clerk named Albert Einstein, you might have heard of him, published a paper on what's known as the photoelectric effect. This phenomenon, where light shining on a metal surface causes it to emit electrons, couldn't be explained by classical physics. Einstein proposed that light, like energy, also comes in packets, which he called photons. This idea, for which he later won the Nobel Prize, further cemented the quantum nature of our universe. Then, in the 1920s, the quantum theory was expanded by the likes of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. They developed the mathematical foundations of quantum mechanics, introducing strange concepts like wave-particle duality and quantum superposition. These theories, though counterintuitive, were backed by robust experimental evidence. Quantum mechanics was not simply a new scientific theory, but a fundamental shift in how we perceive the universe. It challenged long-held beliefs about the nature of reality, leading to philosophical debates that continue to this day. The quantum world is peculiar, often defying our everyday intuition. Yet it is precisely this peculiarity that makes quantum mechanics so fascinating. These groundbreaking discoveries paved the way for the development of the standard particle model. At the heart of quantum mechanics lies the standard particle model, a theory that describes the fundamental particles and forces in the universe. The standard particle model, also known as the Standard Model, is our best attempt at understanding the nature of reality at its most fundamental level. It's like the periodic table of elements, but for particles. This model classifies all known particles into three main categories: fermions, bosons, and the Higgs boson. Fermions are the building blocks of matter. They include quarks, which make up protons and neutrons, and leptons, which include electrons and neutrinos. Each of these particles has a corresponding antiparticle. For example, the antiparticle of an electron is a positron. Bosons, on the other hand, are particles that carry forces. They include photons, which carry the electromagnetic force, gluons, which carry the strong nuclear force, and W and Z bosons, which carry the weak nuclear force. Unlike fermions, bosons do not have antiparticles. Then there's the Higgs boson, a unique particle that gives other particles mass through the Higgs field. Its discovery in 2012 was a significant milestone in the field of particle physics. The standard particle model also identifies four fundamental forces that govern the interactions between particles. These are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the force we're most familiar with, but it's actually the weakest of the four forces. Electromagnetism governs the interactions between charged particles. The strong nuclear force holds the nucleus of an atom together, while the weak nuclear force is responsible for radioactive decay. However, there are still some gaps in the standard particle model. For example, it doesn't explain the nature of dark matter or dark energy, and it doesn't incorporate gravity at the quantum level. But despite these limitations, the model has been remarkably successful in predicting the behavior of particles and forces. With the standard particle model, we have a framework to understand the fundamental particles and forces that make up our universe. Now that we have a basic understanding of the standard particle model, let's delve deeper into the world of particles. The standard particle model, a cornerstone of quantum mechanics, is composed of two key types of particles: fermions and bosons. Fermions are the building blocks of matter. They include quarks and leptons, which are further divided into 6 flavors each. Quarks form protons and neutrons, while leptons encompass electrons, muons, taus, and their corresponding neutrinos. Bosons, on the other hand, are force carriers, the particles that facilitate interaction among fermions. These include the photon, which mediates the electromagnetic force, the W and Z bosons, responsible for the weak nuclear force, and gluons, which carry the strong nuclear force. Then, we have the Higgs boson, an exceptional particle that gives other particles their mass. It's like a cosmic molasses, if you will. As particles traverse through the Higgs field, an energy field filled with Higgs bosons, they acquire mass. The more they interact with this field, the heavier they become. These particles interact with each other through 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Gravity is the most familiar to us, governing the motion of planets and stars. Electromagnetism includes the forces acting between charged particles. The strong nuclear force binds quarks together in protons and neutrons, while the weak nuclear force is responsible for radioactive decay. To sum it up, the standard particle model is like a cosmic Lego set. Fermions are the bricks, bosons are the connectors, and the Higgs boson provides the weight. The fundamental forces dictate how these pieces come together, resulting in the diverse and complex universe we see around us. It's a world of near-infinite complexity, but at its heart it's all about particles and forces, the basic elements of matter and interaction. These particles and their interactions form the basis of the physical world as we know it. How does the standard particle model help us understand the universe? This is a question that intrigues physicists and cosmologists alike. The standard particle model, or the standard model as it is commonly known, is a theory in physics that describes 3 of the 4 known fundamental forces in the universe and the elementary particles that they act upon. It's a fascinating map of the subatomic world, comprising of particles like quarks, leptons, and bosons. These particles and forces form the foundation of matter and energy, the building blocks of the universe. In essence, the standard model is the rulebook of the cosmos. It dictates how particles interact and behave, and these interactions give rise to the structures and phenomena we observe in our universe. From the tiniest atoms to the grandest galaxies, everything is governed by these principles. Quarks, for instance, are the smallest particles we know. They combine in various ways to form protons and neutrons, which in turn form the nuclei of atoms. Leptons, another type of particle, include electrons that orbit these nuclei, forming the atoms that are the basic units of all chemical elements. The bosons, on the other hand, are the force carriers. They mediate the forces that hold these particles together. The photon, for example, is responsible for electromagnetic force, which holds electrons in their orbits around the nucleus. The gluons hold the quarks together within the protons and neutrons. The Higgs boson, discovered in 2012, is also a part of the standard model. It's associated with the Higgs field, which gives particles their mass. This discovery was a significant validation of the model and a monumental step forward in our understanding of the universe. So, you see, this is not just a model. It's a Rosetta Stone of the universe, translating the cryptic language of the cosmos into something we can begin to comprehend. It's a testament to our relentless pursuit of knowledge and our desire to understand our place in the universe. The standard particle model provides the key to unlock the secrets of the universe. So, what's the answer to our initial question? What is the universe truly made of? We embarked on a journey to unravel this enigma, and after a deep dive into the world of quantum mechanics, we have our answer. The universe, in its most basic form, is a symphony of various tiny particles and forces, all of which are eloquently described by the standard particle model of quantum mechanics. We've talked about the birth of quantum mechanics, a revolutionary idea that fundamentally changed our understanding of the universe. We've seen how the concept of particles evolved over time, leading us to the complex but fascinating standard particle model. This model, as we've explored, is not just a collection of abstract concepts. It's a tool, a key to unlock the secrets of the universe. It helps us understand how particles interact, how they form the world as we see it, and even how they might shape the universe's future. But remember, our journey doesn't end here. The beauty of science is its constant evolution. As we continue to probe the mysteries of the universe, our understanding of it will grow and change. The standard particle model is our current best answer, but who knows what exciting discoveries the future holds. Next time you gaze at the stars, remember, you're looking at a universe made of tiny particles and forces, all beautifully described by the standard particle model of quantum mechanics. Now that we've explored the standard particle model of quantum mechanics, what are your thoughts? Do you find it as fascinating as we do? We've barely scratched the surface of this complex and profound area of study. There's so much more to learn, so many more questions to ask, and so many more mysteries to unravel, and that's where you come in. We invite you to be a part of this journey of discovery. Share your thoughts, your ideas, and your questions in the comment section below. We want to hear what you think about this topic. Are there any parts of it that you find particularly intriguing? Are there any aspects of quantum mechanics that you'd like to know more about? Your input will help shape our future discussions, so don't hesitate to share. We're excited to hear your thoughts and continue this quantum journey together. Remember, science is a shared endeavor, and your curiosity is a vital part of that. So let's keep exploring, asking questions, and seeking answers. Together, we will continue to unravel the mysteries of the universe.